I think 52 years journey is over, And on that day, Dr. Narasimha decided we should have one science lecture in a week. So 1 month and 4 witness tests and 3 science lectures, 1 film show. Our start to 52 years, I don't think we'll let go even a single witness day. It's important. Next month program one Wednesday 14th Wednesday birthday, 15th Sankranti anta. Adike mana Friday lecture tanpidinu nodi actually. That is 3 lectures plus 1 film show. Adalle 39 years continuously July 1st to July 31st a science festival 30 lectures 39 years. July 1st to July 31st anta maatra ಹೇಳ್ತೀನಿ year ಹೇಳ್ತಾ ಇಲ್ಲ. ಈಗ ಯಾವ year ಅನ್ನ ಬನ್ನಿ 2020 ಬನ್ನಿ 2030 ಬನ್ನಿ 3000 ಬನ್ನಿ July 1st to July 31st science lecture. That is fixed. Our mark ಬಂದು we are at 2628th lecture, and that lecture is going to be delivered by our own National College student, Professor M.G. Vedavyas, on common sense of science. On behalf of the Bangalore Science Forum, and on behalf of you, and on behalf of me, I extend a very cordial welcome to Professor M.G. Vedavyas.
M.G. Vedavyas and myself studied together in BSc in the same college.
And Dr. Vishaka, they are sitting. I extend a very cordial welcome to both of them. Of course, National College student and bitterne ಹೊರಟೋಗುತ್ತೆ. ನಮ್ಮ ಪುತ್ತಾತ್ನ ಫೋಟೋ ತಗೊಂಡಿದ್ದಾರೆ ಅವರು. That's good. National College is mere ಹೊರಟೋಗುತ್ತೆ ಕಂಪ್ಲೀಟ್ ಆಗಿ ಟೋಟಲ್ ಆಗಿ ಚೆನ್ನಾಗಿ ಅಂತಂದ್ರೆ. In addition to that, after graduating from National College BSc, went on to complete his BE in Electronics and Communication Engineering from Indian Institute of Science. He completed his MBA from the Indian Institute of Management, Bangalore, and then completed an executive education course for global managers from Harvard Business School. So, all tags are National College, Indian Institute of Science, and Indian Institute of Management, Bangalore, second best, third best, whole world. Of course, Harvard and need not speak anything about it. All good tags. Then, he has more than 25 years of industry experience. He was the regional head of TCS in UK and was senior vice president of Mahindra System, responsible for global telecom business before moving into academics. And academics, his love is for teaching, for academics. He has come to that. And he is currently a professor of management at PES University. He teaches strategic management, entrepreneurship development, and international marketing. He heads PES's IT development efforts. He consults for startups and is a visiting faculty at SRM University, Chennai. They have successfully attempted innovative teaching methodologies in entrepreneurship and strategic management. ಅದೊಂದಾಗಿ ನ್ಯಾಷನಲ್ ಕಾಲೇಜ್ ಬಂದಾದ್ರೆ ಇನ್ನೊಂದು ಯಾರು ಗೆಸ್ ಮಾಡೋಕ್ಕಾಗಲ್ಲ. ಈ ಕೌನ್ ಮನೆಗೆ ಹಾಕೋಪತಿಯಲ್ಲಿ 1000 ರೂಪಾಯಿ 1 crore or 5 crore ಪ್ರೈಸ್ ಇರ್ತಲ್ಲ, ಅಷ್ಟು ಪ್ರೈಸ್ ಇಷ್ಟು ಗೆಸ್ ಮಾಡೋಕ್ಕಾಗಲ್ಲ. He has got intimate relationship with the Bangalore Science Forum. ಏನಪ್ಪ ಇಂಟಿಮೇಟ್ ರಿಲೇಶನ್? ಎಲ್ಲ ಲೆಕ್ಚರ್ಸ್ ಅಟೆಂಡ್ ಮಾಡಿದ್ರ ಅದು ಇಂಟಿಮೇಟ್ ರಿಲೇಶನ್ಶಿಪ್ ಅದಲ್ಲ. ರಿಯಲ್ ಥಿಂಗ್ ಈಸ್ he was the secretary of the Science Forum during 85-86. Very interesting, ಇದಾದ್ಮೇಲೆ ನಮ್ಮ ಇದಕ್ಕೆ ಬಂತು ಅಂತಾರೆ ಇವತ್ತಿನ ದಿನ. The students who have won prizes in the 49th annual intercollegiate science contest. 49 years ನಡೆಸಿದ್ವಿ. ಯಾವುದೋ ಒಂದು 49 years ನಡೆಸ್ಬಿಟ್ರೆ ಇಷ್ಟು ಕಷ್ಟ ಅಂತ. ಆದರೆ ನ್ಯಾಷನಲ್ ಹೈಸ್ಕೂಲು 1970 ಸ್ಟಾರ್ಟ್ ಆಗಿದ್ದು. 97 years ಇಂಟರ್ಸೆಕ್ಷನ್ ಡ್ರಾಮಾ ಕಾಂಟೆಸ್ಟ್, ಮ್ಯೂಸಿಕ್ ಕಾಂಟೆಸ್ಟ್, ಡಿಬೇಟ್ ಕಾಂಟೆಸ್ಟ್ ನಡೆಸಿದ್ದಾರೆ. ಒಂದು ವರ್ಷನೂ ಇದಾಗಿಲ್ಲ. ಅರವಿಂದ್ ಕುಮಾರ್ ಯಾಕೆ ಹೇಳ್ತಾರಂದ್ರೆ ನರಸಿಂಹಯ್ಯ ಸ್ಟೂಡೆಂಟ್ ಆಗಿ ಬಂದಿದ್ದು. ಅವ್ರು ಹೇಳ್ತಾರೆ ಒಂದ್ ಕಡೆ, ನಾನು ಏನನ್ನು 1930s ಕಂಡೇನೋ, ಏನ್ ಕಂಡಿದ್ದಾರೋ ಡ್ರಾಮಾ ಕಾಂಟೆಸ್ಟ್, ಮ್ಯೂಸಿಕ್ ಕಾಂಟೆಸ್ಟ್, ಡಿಬೇಟ್ ಕಾಂಟೆಸ್ಟ್, ಅದನ್ನ ಮುಂದೆ ನ್ಯಾಷನಲ್ ಕಾಲೇಜ್ ಬಸ್ಸಲ್ಲಿ ತೊಗೊಂಡೋದೆ, ಜೆಎನ್ಯು ತೊಗೊಂಡೋದೆ, ಬ್ಯಾಂಗ್ಳೂರ್ ಯೂನಿವರ್ಸಿಟಿ ಸ್ಟಾರ್ಟ್ ಮಾಡಿದೆ. ದಟ್ ಈಸ್ ನ್ಯಾಷನಲ್ ಹೈಸ್ಕೂಲ್. ಅಂದರೆ 97 ವರ್ಷ ಕೆಳಗಡೆ ಇಂಟರ್ಸೆಕ್ಷನ್ ಡ್ರಾಮಾ ಕಾಂಟೆಸ್ಟ್ ಮಾಡಿದಾಗಲೇ ಇಸ್ ಮೈಂಡ್ ಬಾಂಬಿಂಗ್ ಆ್ಯಕ್ಚುಲಿ ಗೊತ್ತಿಲ್ಲ. ಹಾಗೆ ಇಲ್ಲಿ ಬಂದಾಗ 49 ಇಯರ್ ಆ ಸ್ಟೂಡೆಂಟ್ಸ್ ಎಲ್ಲ ಬಂದರೆ ವಿನ್ನರ್ಸ್ ಅಂಡ್ ಆಲ್ಸೋ ದರ್ ಪೇರೆಂಟ್ಸ್. ಇನ್ಸಿಡೆಂಟ್ಲಿ ವೇದವ್ಯಾಸ ಬೇಕಾದಷ್ಟೇ ಆ ಕಾಂಟೆಸ್ಟ್ ಪಾರ್ಟಿಸಿಪೇಟ್ ಮಾಡಿ ಇವಾಗ ನಡೀದೆ. ಈಗ ನಾನೇ ಟೀಚರ್ ಆಗಿ ನಾನು ವೇದವ್ಯಾಸ ಕೇಸ್ನಲ್ಲಿ ಅಫ್ಕೋರ್ಸ್ ವೆರಿ ಚಾರ್ಮಿಂಗ್ ಪರ್ಸನಾಲಿಟಿ ನೋಡೋದು ಗೊತ್ತಾಯ್ತು ಆ್ಯಕ್ಚುಲಾಗಿ. ಅಪಾರ್ಟ್ ಫ್ರಮ್ ದಟ್ ಹಿ ಹ್ಯಾಸ್ ವನ್ ಮೆನಿ laurels for the college and a good student in the college and a science form secretary ಎಲ್ಲ ತಿಳ್ಕೊಂಡಿದ್ದಾರೆ ಟೋಟಲ್ ಆಗಿ. and even now he takes interest. ನಾವು ಕರೆದಾಗೆಲ್ಲ ಬರ್ತಾರೆ and will suggest different ways and means. and also YMN Murthy endowment prizes. YMN Murthy ಅಂದ್ರೆ ಗೊತ್ತಿರ್ಬೇಕು ನಿಮಗೆ. ಅವಳೇ ಫಸ್ಟು ಎಗೇನ್ ಗೋವನ್ ಹ್ಯೂಮನ್ ಕ್ಲಬ್ ಯಾವಾಗ ಸ್ಟಾರ್ಟ್ ಮಾಡೋದು ಗೊತ್ತೇನೋ, ನಾನು ಮುಗಿದಾದಾಗ ಈ ನ್ಯಾಷನಲ್ ಕಸ್ಕೊಂಡ ಇದೆ ಆವಾಗ ಸ್ಟಾರ್ಟ್ ಮಾಡೋದು. ನಾವೇ ದುಡ್ಡು ಕೊಟ್ಟು ನ್ಯಾಷನಲ್ ಕಾಲೇಜ್ ಎಂತ ಅದ್ಭುತ ಅಂತ ಅದಕ್ಕೆ ಜಾಗ ಕೊಟ್ಟರು. ಅವಾಗೆಲ್ಲ ನರಸಿಂಹನ ಹಾಸ್ಯ ಮಾಡೋರು. ಇವಾಗ ಸೈನ್ಸ್ ಫಾರ್ಮ್ ಸ್ಟಾರ್ಟ್ ಮಾಡಿದಾಗ ನರಸಿಂಹನ ಹಾಸ್ಯ ಮಾಡೋರು. ಯಾಕಂದ್ರೆ ನಾವ್ಯಾರು 3 ಜನ ಕೂತ್ಕೊಳ್ತಾ ಇದ್ವಿ ಬಂದಲ್ಲಿ. ಇಂಥ ರೂಮ್ ಅಲ್ಲ, ಯಾವುದೋ ಒಂದು ರೂಮ್ ಒಳಗಡೆ. ಅವ್ರು ಹೇಳೋದು ಇಲ್ಲಪ್ಪ ಕರೆಕ್ಟಾಗಿ ಮಾಡ್ಕೊಂಡಿದ್ರೆ ಬದುಕತ್ತೆ ಅಂತ. ಇವತ್ತೇನ ಈ ರೂಮ್ಗೆ ಡಾಕ್ಟರ್ ನೆಗೇಶ್ ಅಂತ ನೋಬೆಲ್ ಲಾರೆಟ್ ಮಾಡಿದ್ರು, ಹೂ ಗಾಟ್ ದ ನೋಬೆಲ್ ಪ್ರೈಸ್ ಆನ್ ಚೀ ಕಪಲಿಂಗ್ ಇನ್ ಪಲೇಡಿಯಂ. ಬಂದಿದ್ದಾಗ ಇಲ್ಲಿ 200 ಜನ 6 ತಿಂಗಳಿನ ಕಡೆ ಔಟ್ಸೈಡ್ 1200 ಜನ ಚೇಂಜ್ ಸ್ಟ್ರೀಟ್. ಆವಾಗ ಇಬ್ಬರೇ ಕುತ್ಕೊಂಡ ಜನ ಹಾಸ್ಯ ಮಾಡ್ತಾರೆ ಸೈನ್ಸ್ ಫಾರ್ಮ್ನ ಆ ಲೆವೆಲ್ಸ್ಗೆ. ಅಂಡ್ ಜೋನ್ಸ್ ಹಾಕ್ಕೊಂಡು ಬಂದಾಗ ನೋಬೆಲ್ ಕರೆಂಟ್ ನೋಬೆಲ್ ಲಾರೆಟ್ 2012 ಫಿಸಿಯಾಲಜಿ ಅಂಡ್ ಮೆಡಿಸನ್ 4,000 ಮೆಂಬರ್ಸ್ ಅಂದರೆ ಸೈನ್ಸ್ ಫಾರ್ಮ್ ಲೆವೆಲ್ ಲೆಕ್ಕ ಹೇಗೆ ಹೋಗಿದೆ ಅಂತ ಹೇಳಿ ಟೋಟಲ್ ಬಂದಾಗ. ಸೊ ಆ YM ಮೂರ್ತಿ ಅವ್ರದ್ದು ಅವ್ನು ಬಾ ಅಂತ ಕರಿತೀನಿ, ಬಂದುಬಿಟ್ರೆ ನನಗೂ ವೇದವ್ಯಾಸಕ್ಕೆ ಅವಕಾಶ ಇರಲ್ಲ. ಏನಾಯ್ತಲ್ಲ 95 ಫಸ್ಟ್ ಕ್ಲಾಸ್ ಮಾತಾಡ್ತಾರೆ ಅಂದರೆ 95 years ಹ್ಯೂಮನ್ ಮೇಲೆ, ನಾಟ್ ಆನ್ ಸೈನ್ಸ್. ಯಾಕೋ ವಿಲ್ ಎಂಜಾಯ್. ಅವರು ನೋಡಿ ಎಂಡೋಮೆಂಟ್ ಪ್ರೈಸ್ ಕೊಟ್ಟಿದ್ದಾರೆ. ಅದು ಎಕ್ಸಾಕ್ಟ್ ರಿಕಾಲ್ ಮಾಡಿ ಪಡೆದರು. ಇದನ್ನು 40 years ಕೊಟ್ಟಿದ್ದಾರೆ ಕನ್ನಡ ಆ್ಯಕ್ಚುಲಿ YMN ಮೂರ್ತಿ. ಆಮೇಲೆ ಇಂಟರ್ನ್ಯಾಷನಲ್ ಹ್ಯೂಮನ್ ಕ್ಲಬ್ ಆಯಿತು. ಆಮೇಲೆ ಇವರು ಹಾಸ್ಯೋತ್ಸವ ಅಂತ ಮಾಡ್ತಾ ಇದ್ದಾರೆ. ಅವರಲ್ಲ ಬೇರೆಯವರು, ಅಂದರೆ ಯಾರ್ಯಾರು ಹಾಸ್ಯೋತ್ಸವ ಮಾಡಿದ್ರೆ ಅವರೆಲ್ಲ ದೇ ಡಿರೈವ್ಡ್ ಇನ್ಸ್ಪಿರೇಷನ್ ಫ್ರಮ್ YMN ಮೂರ್ತಿ. ಇದೆಲ್ಲ ಆದ್ಮೇಲೆ ಮೊನ್ನೆ ಸಮಯಕ್ಕೊಂದು ಸುಳ್ಳು ಅಂತ ಡ್ರಾಮಾ ಆಯಿತು, ನಮ್ಮ ನ್ಯಾಷನಲ್ ಕಾಲೇಜ್ ಬಸ್ ನೋಡಿದೆ. ಆರ್ಗನೈಸರ್ಸ್ ಹಾಸ್ಯೋತ್ಸವ ಬೇಲೂರು ರಾಮಮೂರ್ತಿ ಹೇಳಿದ್ರು, ಸರ್ ನಮ್ಮ ಹಾಸ್ಯೋತ್ಸವಕ್ಕೆಲ್ಲ ಚೆನ್ನಾಗಿದೆ ಸರ್ ಅಂತಾರೆ. ಅಂದರೆ ನಮ್ದೆಲ್ಲ ಕೂತ್ಕೊಂಡೋಗ್ತಾ ಇಲ್ಲ. ವಯಸ್ಸಾದವ್ರು ಬಂದರೆ ಗೋವಿಂದ ಆಗೋದಷ್ಟೇ ನಕ್ಕು ಆಲ್ ದಿ 90 minutes. ದಟ್ ಇಸ್ ಫ್ರಮ್ ಶಿವರಾಮ್ ಬಾಬು ಹಿರಟ್ಟಯ್ಯ ಎಲ್ಲ ನಮ್ಮ ಸ್ಟೂಡೆಂಟ್ಸ್ ಕಂಪ್ಲೀಟ್ ಅಂತ ಇರೋ ಆ ಪ್ರೋಗ್ರಾಮ್ ಇದೆ. ಹಾಸ್ಯೋತ್ಸವ ಅವ್ರಿಗೆ ಡೊನೇಟ್ ಮಾಡಿದೆ ಅಂತಾರೆ. ಇದಾದ್ಮೇಲೆ ನೆಕ್ಸ್ಟ್ ಇಯರ್ ಏನು ಸರ್ ಒಂದು ವರ್ಷ ಸುಮ್ಮನೆ ಇರ್ತಾರೆ ಅಂತ ಕೇಳ್ಬೋದು. ನಾಳೆ ಬಂದ್ಬಿಡುತ್ತೆ ನೆಕ್ಸ್ಟ್ ಇಯರ್ ಆಗ್ತಾ ಇದ್ದೋ. ನೆಕ್ಸ್ಟ್ ಇಯರ್ 2nd January ಯು ಹ್ಯಾವ್ ಗಾಟ್ ಒನ್ ಆಫ್ ದಿ ಐ ಥಿಂಕ್ ಬ್ರಿಲಿಯಂಟ್ ಮೋಸ್ಟ್ ಇಂಪಾರ್ಟೆಂಟ್ ಲೆಕ್ಚರ್. ನನ್ನ ಪ್ರಕಾರ ನನ್ನ ಸ್ಟೂಡೆಂಟು ಡಾಕ್ಟರ್ ಎಸ್ ಸೀತಾರಾಮಯ್ಯ ಅಂತ. ಪ್ರಪಂಚದ ಪ್ರಕಾರ ಇಸ್ ವೆರಿ ಡಿಸ್ಟಿಂಗ್ವಿಶ್ಡ್ ಪ್ರೊಫೆಸರ್ ಟು USA, ರೈಡರ್ ಪ್ರೊಫೆಸರ್, ಡೈರೆಕ್ಟರ್ ಫ್ಲಾರಿಡಾ ಇಂಟರ್ನ್ಯಾಷನಲ್ ಯೂನಿವರ್ಸಿಟಿ. ಅವ್ರು ಏನು ಹೇಳಿದ್ರೆ, ಬನ್ನಿ ಗೋಪಾಲ್, ಲೂಸಿಯಾನಾ ಸ್ಟೇಟ್ ಯೂನಿವರ್ಸಿಟಿ ಅಂತ ಇಲ್ಲ, ಅಲ್ಲಿ ಕಂಪ್ಯೂಟರ್ ಸೈನ್ಸ್ ಡಿಪಾರ್ಟ್ಮೆಂಟ್ ಇರಲಿಲ್ಲ 35 years ಬ್ಯಾಕ್. ಇವರೇ ಸ್ಟಾರ್ಟ್ ಮಾಡಿದ್ದು. ಅವ್ರ ರ್ಯಾಂಕಿಂಗ್ ಅದಕ್ಕೆ ಪ್ರಪಂಚದ 1000 ರ್ಯಾಂಕಿಂಗ್ ಇತ್ತು. ಬಟ್ ಇವರು 25 ವರ್ಷ ಕೆಲಸ ಮಾಡಿ 20th ರ್ಯಾಂಕ್ ತಗೊಂಡ್ರು ಕಂಪ್ಯೂಟರ್ ಸೈನ್ಸ್ ಡಿಪಾರ್ಟ್ಮೆಂಟ್. ಆಮೇಲೆ ಫ್ಲಾರಿಡಾದ ಬಂದಿದ್ದಾರೆ. ಕಾರಣ ಅಂದರೆ ಅವ್ರು ನಾಸಾ ಪ್ರೊಫೆಸರ್ ಹೋಗೋದು ಆ ಕಾಂಟ್ಯಾಕ್ಟ್ಸ್ ಇಂದ. ಅಂಡ್ ಈ ಸ್ಪೀಕಿಂಗ್ ಆನ್ health information technology, big data analytics. You kindly carry this message that this science form is active and this subject is such a wonderful, important subject currently, totally. ಅವ್ರು ಬರ್ತಾರೆ ಫ್ರೈಡೆ, ಇವೆಲ್ಲ ನೋಡಿ ಅವ್ರನ್ನ ಆ ಇನ್ವಿಟೇಷನ್ಸ್ ಇದೆ. ಮುಂದೆ ಡಾಕ್ಟರ್ ಲಕ್ಷ್ಮಣ್ ಅಂತ ಫಿಸಿಕಲ್ ನ್ಯೂಟ್ರಿಷನ್ ಲೆಕ್ಚರ್ಸ್ ಇದೆ. ಒಂದಿನಾನು ಸ್ಟಾಪ್ ಆಗೋದಿಲ್ಲ. Come on Wednesday, there's some lecture and you'll enjoy. The lecture is on science. If there's a film show, there's a film show on science subject. ಯಾಕೆ ಹೇಳ್ತಾ ಇದ್ದೆ ಅಂದರೆ, ಬೇಕಾದಷ್ಟು ಡಿಫ್ರೆಂಟ್ ಕಾಲೇಜಸ್ ಬಂದಿದೆ. ಈಗ ಬೆಂಗಳೂರು ಕಾಲೇಜ್ ಅವೆಲ್ಲ ನಾವು ಹೋಗಿ ಬಿಗ್ ಡೇಟಾ ಅನಾಲಿಟಿಕ್ಸ್ ಅಂತ ಹೇಳಿ ಈ ಎಲ್ಲ ಸಾಫ್ಟ್ವೇರ್ ಇಂಜಿನಿಯರ್ಸ್ ಇರೋ ತಕ್ಷಣ ನಾನು ಬರ್ತೀನಿ ಅಂತ ಹೇಳ್ತಾರೆ ಟೋಟಲ್ ಆಗಿ. ಸೊ ವಿತ್ ದಿಸ್ ಇಂಟ್ರಡಕ್ಷನ್ ಟುಡೇ ಐ ರಿಕ್ವೆಸ್ಟ್ ಅವರ್ dear student at National College, Prof. Vedavyas, to deliver the lecture on common sense of science. Please.
Thank you, and I think because I have known AHR for a very long time, I think he eulogized me much more than is real. Okay, we will of course speak a little about reality and what is not reality here. So it's great to come back to Science Forum. This completely different platform now than what it used to be. We used to conduct most of the lectures in a much smaller room with none of these audio-visual facilities. So it's always great to see this kind of a change. And yes, I always felt very proud to have represented the college in many lecture contests. It was always very exciting, and we always felt that most of the learning that still, whatever little we can still remember, came from those lecture contests, and not so much from the classes, because you could always read the textbook and get the marks. Even during that time, I used to have, in the college, of course, many friends who used to accompany me to the lectures, clap and give me encouragement. And today I'm happy to have two of those friends who are still come today for my lecture, Narendra and Vishwanath. Thank you very much for coming there after 40 years. So that's very nice. So what I will do today is, first of all, I have to admit that I'm not a scientist. Okay, so though I have studied in IISc, I teach management. I'm an MBA, so I think I forgot a lot of my engineering the moment I stepped out of the gates of IISc. But I have continued to have an interest in science, so to say, and I admire the scientific method, the scientists, what they have achieved, and so on. What I will do today is try to keep this lecture about the common sense of science at a high school PUC level. So if there are people among you, stalwarts among you, who know science to a much higher level, you may not find it too much in-depth, so to say. But I've always had an interest in science, and my whole point is that most of you, whether you continue to be in science, whether you go to engineering, medicine, arts, literature, or whatever, I would like all of you to continue to have some kind of interest in science, because some of the things that when you read about science can be so exciting and so fulfilling that it kind of enhances, I believe, your quality of life. That's the only reason. So I will speak for about 20 minutes or 30 minutes. And we can have an interactive session for about 10 minutes or so. What I will do is I will just initiate some of the scientific methods, principles, by taking you through a storyline. I'm not going to cover everything in the history of science over the many centuries that has happened, but take a few threads, here and there, just to illustrate some of the principles of scientific method, and also how scientific method itself has changed over a period of time. Okay. So what we will cover is, what does the scientific method really involve? Does it make common sense? Sometimes we think that science is somehow outside our realm. The scientists sit, they have some lab coats and do some wonderful stuff which we don't understand. It's not so. Okay, if you really read, if it's taught the right way, I'm sure every one of us can understand science. And how has our own understanding of the nature of reality, especially, how has it changed over a period of time? And as I said, we will cover it by looking at a few milestones in the history of science. So going back to a bit of history, science has always been about understanding nature. Whether you look at Aristotle or Plato and Socrates before him, it's always about understanding nature. Or even whether you look at our own Indian scientists like Varaha Mihra or Bhaskara or anybody, they have all tried to understand nature and describe it in a way which can be useful to mankind. Collect knowledge, use that knowledge to invent tools and make human life more qualitative. So that has always been the nature of science, and it has been that even today. So whether you take catapults were invented by Archimedes, using which they tried to use it as a weapon by throwing fireballs using a catapult towards the enemy. So it has always been a bit political, bit philosophical, a bit of religion, all coming together in the development of science. Or whether it is poisonous spears, or whether it is, I'm sure you have all heard of the phosphorus and iron mixed pillar in Delhi near the Qutb Minar, which is rust proof. Even after almost more than 1,000 years, it is still not rusted, and it's made of iron. So people have always experimented and invented things in order to enhance our knowledge of nature and trying to manipulate nature to help mankind. Or if you look at seafarers, which is where astronomy started, when in the late 1400s, when people started going out in the sea and discovering new lands, what did they want? They wanted to make sure that they know where they are on the sea, right? There was no mariner's compass yet. So they could only look at the stars and try to map the stars to find out where they are and use that as a navigation aid. That's how astronomy developed in a big way. Mathematics related to astronomy developed in a big way. And we have heard of mathematicians of, whether in India, Egypt, Babylonia, and other places, who have been great mathematicians. In fact, the Indian mathematicians' concept of time has been unmatched anywhere in the world. Their idea of the Kalpa, the Yuga, Manvantara, all these things have been fantastic. No other civilization has been able to think of time in such huge quantities. So, irrespective of the country, Greeks, Babylonians, Egyptians, Indians, there have been great thinkers, great mathematicians, experimenters, and so on. Okay? So what have they all done? They have all developed knowledge, quest for truth, ultimately. Whether you look at philosophy, religion, science, it's all quest for truth. Maybe in their own way, in their own framework, in different ways, but they all merge where the quest for truth is concerned. I would like to warn you that when we talk of scientific thinking, it is not just about science. Of course, science progresses through scientific thinking, through experimentation and so on. But scientific thinking goes beyond that. Scientific thinking is a methodology or a framework that you use, which is a series of steps that you use to arrive at a knowledge which is verifiable. And that's what we will go through in most of the lecture today. The first point about scientific method is that it is empirical. What do we mean when we say it's empirical? It's empirical meaning it is based on lots of observation of facts. Whether you take Aristotle's idea of human beings, or if you take Ayurveda, Sushruta, or any other great Indian medicine people, they always thought, based on the reality which is around them, what do you find around you? Air, water, earth, sky, right? So they thought obviously that everything consists of these four things. So Aristotle thought the same thing. It's not very different from what the Indian scientists thought. So what we try to do here is we try to look at the nature around us and try to order it in a way which makes sense to us. This is what has happened always in science. It has not changed in thousands of years. We'll see some examples as we come later. In fact, science was, even as a word, science came much later. Science has not been different from philosophy or religion. That's why even today when people get a PhD, it's called Doctor of Philosophy. Why is it called Doctor of Philosophy? Because it is philosophy is again the quest for truth, of trying to understand nature that much more. Okay. So it was only after 1500 AD that science became different from religion, because science started getting more and more outside the church and the religious part of it, and started becoming more experiment-oriented, so to say. Okay? And what was considered as common sense at that time? So you could say, for example, Aristotle tried to differentiate animals in two ways. One, those which have red blood, those that don't have red blood. And he felt that the nature of these two things are very different. Whether it was right or wrong is different. But the idea is that you try to look at things around you, try to order it in a certain way, try to study it more and add to the body of knowledge. Or for example, that stars and planets revolve around the earth. And, earth was the center of the universe and the stars and planets were in some 10 crystal spheres around. Now it looks silly. But if you lived in that age, that would have been common sense. Right? I mean, how can you argue if somebody says the earth is flat, if you did not have all these technologies to go out and look at earth as being round? That would be common sense. So we'll see how what we think as common sense has changed because of science over a period of time. So these are what we call the Aristotelian view, which was to do with essentially the Greek scientists' views. Okay? The biggest things that happened when people started going out to other countries using sea was that geometry, which was again the Euclidean geometry coming from Greece, where Euclid started with a set of axioms and built a whole branch of mathematics which could help in calculations, in building the pyramids, in calculating the distance from distance of the planets from the earth and so on. That grew tremendously. And astronomy grew along with that because astronomy was essential to people to do business. So the kings and the queens spent a lot of money on scientists who are developing astronomical calculations because that would help them increase their trade with other countries. Okay? So based on these calculations, people like Galileo, Copernicus, Ptolemy and many other people did these calculations and finally found that Earth is not the center of the universe, nor is it flat, but Earth actually goes around the sun. So the common sense now is different, right? Because now the Earth is going around the sun, and the church could not even agree that it could be so. In fact, the first characteristic, therefore, of scientific thinking is that your conclusions should be based on observation and facts. Because the common sense will change as you observe more and more. So the question is, this is where religion and science became separate. Because the church could not agree that Earth is not the center of the universe. How could God create something? God has created human, who is the highest evolved being, and he is on Earth. How can Earth not be the center of the universe, they asked. But calculations showed that, no, sorry, Earth is not the center of the universe. And for saying so, this is the only photo I have put up in the presentation because I feel sorry for this man, Galileo Galilei. Because for saying that Earth is the center, Earth is not the center of the universe, but it's a heliocentric universe. This man was first, in fact, he was condemned to death, but finally they put him only under house arrest, and he had to publicly take back some of the statements he had made, saying that Earth is not the center of the universe. So he had to retrace and say, I'm sorry, I said this, because that was what was called heresy. That is, speaking something which the church did not believe in was punishable by death. Okay, so the common sense was not as common as we think it is now. To us today, sun being the center of our universe, or at least of our galaxy, is common sense. But then it was not. And people like Galileo have paid a price for it. The other important concept in scientific thinking is the idea of order. Like I said, at the Aristotelian time, they thought about earth, fire, water and sky. However, going back to what Galileo, Copernicus, Ptolemy and others did, they could calculate the distances and other things. They knew that the planets were revolving around the sun. But what they could not say was, how does it do it? Why do these planets revolve around the sun? Is it just God put them there and they are revolving, or is there some other reason? Is there a cause? Is there a reason why this is happening? So before Newton came, so all these people, Galileo, Ptolemy, Copernicus, all these people lived before Newton came. And at that time, before Newton came, if you ask the question, why does the apple fall down? The Aristotelian view was the apple falls down because it is the nature of the apple to fall down. So each thing, each material had a nature, and that nature decided what that material will do. In fact, what we call is inductive reasoning, it is not just that the apple that you see falls down, but every apple, everywhere, will always fall down. In fact, all fruits always will fall down. That's called inductive reasoning, because it is the nature of those things to fall down. Now, this is where the greatness of Newton comes. Okay, and anyway, before going to that, so the idea of order, what is order? How do we look at things and classify them into things? That is the idea of order. That is the second most important concept in scientific thinking. What Newton saw was the order, the same order in gravitation, in the rotation of the planets around the sun, as well as in falling of the apple. That's the greatness of Newton. He, by his thought, by thinking, by looking at those observations, he concluded that gravitation is the cause, and he could explain through his gravitation as the cause why the apple falls down, why the waves are very high during the full moon, why the planets revolve as they revolve, why do planets sweep equal areas in equal amounts of time when they go around the sun. That is the greatness of Newton, connecting the universality of things. Okay? So, when he explained it, it became very obvious to everyone, because he could calculate and show it that this is how it is. But again, the church had a problem. The church said, are you saying that these are all deterministic? That is, can you tell me that tomorrow this is going to happen? This is where each of these planets will be. That means you can calculate. It's not willed by God, but you can actually calculate and show this to me. This is the next problem. Okay? But the greatness of Newton again lies in carrying the earlier work beyond geometry into physics. So earlier the calculations were all geometry based, but he carried it into physics and said that the same cause of gravitation causes all this motion. And in fact, I'm glad to see this shield here, which shows F is equal to ma, which was derived by Newton, based on, and when Newton lived in the 16th century, and that equation has still not changed, and that is universally applicable. So without even going to Mars, Neptune or Pluto, I can say that F equal to ma will hold in that universe also, in that planet also. That is the greatness of some of the scientific thinking. Then, so Newton spoke about the effect, the cause and effect. So there is a cause, gravitation is the cause, the effect is the motion. That becomes a cause for some other effect. So this whole idea of cause and effect made the universe, according to him, a deterministic thing. So if you know the cause, you know the effect. If that is the cause for the next one, you know the effect. That means I can say what is going to be the planetary positions 10 years from now, 100 years from now, 1000 years from now. Similarly, I can go back and say where things were. So he said it's a deterministic world. Everything is determined. Right? So this is the reason that the whole world works like a clockwork. This is the greatness of Newton's work. At the end of the day, he said it doesn't matter where you go in the universe. These equations will hold. And you have all studied those equations. Very simple, straightforward equations. Any of you can solve those equations, right? So it was so graspable and universal, and scientists, during those days, felt that it is so straightforward. It looks like everything has been answered. We don't even have work. Everything has been answered. Newton has said this. It is verifiable, deterministic world. Everything is, we can calculate everything. So what more is there to find out? In fact, John Milton, who was a great poet at that time, has written a poem in which, I'm sure you have heard this, he said, God said, let Newton be, and all was light. That means Newton had given all the answers. Okay? Is it so? So, what was Aristotelian common sense, which, and what was common sense during Galileo's time, for which he had to pay a price, now the common sense has changed to something different now. Okay? So this this cause and effect was the basis of scientific thinking during the 17th and 18th centuries, and it also led to the invention of the machine and so on. Okay, in fact, Newton almost said the universe is like a machine, because like a clockwork, it works. You know, we know what will happen, just like a machine. Machine not in the sense of levers, pulleys and gears, but as a concept. Okay. So if you see, now we have arrived at the scientific thinking where things are rational and empirical. Empirical meaning based on observation and facts. So it is thought, thinking of the type of Newton, plus facts which you can observe. Theory and experiment. In fact, if you see Newton's work, some of his work on optics, where he has done experiments in optics, is some of the greatest contributions to the knowledge of science. So the third characteristic of scientific thinking is that scientific thinking involves all these things. Now, the next important thing. So, if there is order, and you have chosen the order in the right way, if there is cause, if there is effect, can you predict what's going to happen? Which Newton did, and it was verified. And prediction is the next most important concept in scientific thinking. Based on all your observations, you build a model, right? Whether that model is really true or not, we don't know. But that model gives you steps through which to work your postulates, gives you a predictability to the output, which you can measure and see in the real world. Right? If you're going in a car, if you feel that it's going in the wrong direction, you are taking that data in, moving the steering, right? And the car will change the direction. So, somewhere the model that is built into the car is such that you can predict the output when you move the steering. That is part of the scientific thinking. So, the beauty of scientific thinking is just not in observing facts, putting them into order, saying cause and effect, but in its ability to predict what's going to happen based on this model, and whether that happens or not in the real world, which is there for all of us to see. If based on the gravitational theory, if Newton has said that the tides will rise on a full moon day, it is something that you can see. And if he can explain that these are the steps through which it goes, and therefore this happens, unless you can come up with a better explanation which fits all the data, you have to accept whatever data has been given to you, whatever model has been given to you. Okay? So the consequences of model should fit the real world. So predictability based on model, this is another classic step in common sense of science. So now, let's very quickly recap before going into some more, what I would say, very different things. In fact, when we studied physics, this is pretty much, where we stopped, saying that order, cause, effect, prediction, that was it. Okay? So what we are saying is any new model that you come up with has to fit all the old facts, right? If you say that this model is not right and you come up with a new model, it has to explain all the old facts and should predict the new things which you can observe. For example, anyway, these are all straightforward, I will not explain this too much. The important concept of cause and effect is that the present influences the future. That's important. That's the whole idea. And more importantly, determines it. This was what was different as we move to the next century. That's why it's a very important point. Okay. So by the time we reached, Newton, from the world of free will, as we call the Aristotelian one, where things had a will, we come to the world of deterministic machines. But then what happened? Now that Newton had given such a great solution to all the calculations, to all the design of the world, science became, Newton's laws quickly became so popular, and people felt there is nothing more to do, that the scientists themselves became prisoners of that thought, that there is really nothing more to do. Okay? And science really did not progress from that point of view during the next couple of centuries. But away from all this Newtonian astronomy and mathematical calculations and all that, there were people like Priestley, Linnaeus, if you heard of Linnaeus, who did the ordering of the living beings, and Darwin, who did almost 7 years of collecting 17 years of collecting lots of data to classify living things, and then came up with this theory of evolution. The theory of evolution was actually there even before him. His grandfather himself had worked on it. But what Darwin really did was to come up with the survival of the fittest theory. Okay? And he spoke about chance, how mutation can happen, and how chance can make people, make animals or living things more adaptable, and how is it that they survive. Okay, so he spoke about mutation and survival of the fittest. Okay, so did Priestley. Why I have mentioned Priestley is, you have all heard about the equation of, at a constant temperature, if you double the pressure, right, the volume will decrease. Right. So you know those equations. So we will come to some of that equation a little later. Just hang on for a minute. Okay. But again, we come back to the idea of order, because this is again important as we come to the 19th century. Okay. Now, what happened with Newton was, since everybody thought that Newton had explained everything, the problem was that they tried to force an existing system on a set of observations, whether or not that fitted it. So, lots of observations. When you do lots of observations, this is what Darwin, Linnaeus, and other people did. When you do lots and lots of observation, then you try to start categorizing things. And when you categorize things, then, for example, if you do lots of observations on fever, in our world, I'm sure if you go to Sushruta or something, they would have done a lot of observations on fever. And then they would have said, this is Pitta, this is Vata, they would have done their own classification based on observation. So similarly, any observation leads to categorization. So what we used to be called just fever is now there are hundreds of types of fevers, because we have observed lots of facts. Okay? So 18th century was marked by great order, by categorization of lots of observations. I would particularly like to mention Mendeleev. When there was lots of elements were discovered, but what Mendeleev did was to find an order by putting them according to their atomic numbers, and then said there are so many gaps. Okay, and he said all these gaps are to be, there are new elements which are to be filled in these gaps. He said this is the order in which nature exists. This is reality. And the moment Mendeleev came up with this periodic table, within 30 or 40 years, most of the other elements were discovered, because people started looking for them. So that is the greatness of some of these people. Okay, Dalton, Davy, Faraday, I'm sure you have heard most of these names. Then came machines, the Industrial Revolution, all that, all because of order. So, but then, what was common sense immediately after Newton was, again changed in the next century, in the last century. Soon after Newton, when they were calculating the Uranus, the planet Uranus's calculations, the periods that it takes to go around the sun, there was a time when Uranus's times did not match what was predicted by Newton. So, only two things can happen. Either there is a planet whose gravitational effect is causing Uranus to go away into a different orbit, or Newton's theory is wrong. Right? But it so happened that that's how they found the planet Neptune. And they found that if you now take Neptune into consideration, then the Uranus calculations are okay. It still goes by Newton's classical mechanics. But around 1900, the same thing happened with Mercury. This time, there was no Neptune or no other planet to come to the rescue of Newton. So this time, Einstein had to come in. And he had to explain that, sorry, Newtonian mechanics is not all that right, not that common sense that we are all thinking, but there is a problem in Newtonian mechanics. So he said, we have always considered space and time as two different things. You can two absolute things. But he said these are actually they're kind of connected in a very complex way. So for somebody who is in some other universe, some other planet, if you look at especially at speeds which are closer to the speed of light, the events that you observe in sitting in Earth could be different from the sequence of events that you are observing from somewhere else, or the time lag between them could be very different. So what does this mean? This means the whole cause and effect theory is gone. This cause giving rise to effect, giving rise to the next effect is now under question. This doesn't look like common sense to us. But scientists had no choice but to accept that that is the common sense, because Einstein's theory was tested by the deviation of the sun's rays around Mercury in 1904 or whenever that was, and he was proved right. So when the fact of observation of Mercury does not fit all the earlier models of Newton, but here is a new model of Einstein which explains everything which was the earlier facts and the new fact which was not explained by Newton's model, Einstein's model has to be right. So this is the greatness about scientific thinking. No matter, no doubt Newton was a great scientist, but if he was wrong somewhere, he was wrong. So you have to relook at the space-time relativity. That's where relativity came. Okay, and you had to, so they came up with a new model. So then of course there was a second difficulty, which was the photoelectric effect, the quantum mechanics. So photoelectric effect was about, if you're going in a bicycle, if you take the light, the tungsten, not these, but the old type of tungsten filament light, if the temperature increases, it gives more light, but also the color of the light changes. So they started trying to find out why does it change, and then they got into quantum mechanics. They said, while light is not, earlier that Newton had said, it was particles, then Huygens had said it is wave theory, it is like a wave. Then again, this light thing, again they had to say, no, it's not really a wave, but it can be a particle sometimes, a wave sometimes. No, that's not common sense. How can light be a wave sometimes and particle sometimes? Does it have a mind of its own to suddenly become a particle when it wants to, suddenly become a wave when it wants to? That's not true. So they made a lot more. In fact, photoelectric effect itself was found by Einstein, another great contribution. In fact, he was given Nobel Prize for photoelectric effect, not for relativity, all that. Okay? So they had to explain something funny, they had to start saying that this whole electron thing is like a cloud, it can be here, it can be there. You can never say where it is. You can only give a probability. You can say it's 80% chance that it is here, but a 10% chance that it is somewhere else. So this idea of chance. So idea of chance was very, very difficult for us to accept, because after having accepted cause and effect, which is very deterministic, accepting idea of chance became very difficult. But it is like, to give you an analogy, it is like the tossing of a coin. You know that if I do 500 trials, mostly I can say with a high degree of confidence that 250 will be heads, 250 will be tails, right? You don't need to actually do tossing of the coin 500 times to say that. But can you say after 500 what the 501st will be? Can you guarantee that will be a head or a tail? No. That is chance, right? So they said, if that you can understand, or take the population for example, I can't say which married couple is going to have a child next year, but I can still predict that the growth rate, population growth rate of India is going to be so much, right? That is the idea of being able to statistically predict something, unable to guarantee in a particular case, right? So that's the idea of chance. So you could only give a probability of where an electron lies. So the deterministic world of Newton was shown to be inapplicable, especially in the subatomic world. It still works at the macro level, but at the subatomic world, it doesn't work. Okay? So if you have heard of Heisenberg's uncertainty principle, what does it say finally? It says every description of nature, because whether you talk of planets, astronomy or whatever, they are all made up of the same electrons and protons, where we are saying things are uncertain. So if things are uncertain at the electron level, at the subatomic level, at the atom level, then how can they be certain at the macro level? That was the question. So the theory of chance tells you, I mean, you can prove that through quantum mechanics, that while it may not work at the subatomic level, when you aggregate them, it works, like the analogy I have given you about the population or about radioactivity, for example. Radioactivity, you know about the half-life. If you have a radioactive element, if the half-life is 5 years, what does it mean? After 5 years, if you have 1 kilo of the radioactive material, after 5 years, only half of it will remain. But you can never say which half. Right? You don't know which of those atoms will radiate out and die. So that is the idea of chance. That means, idea of chance doesn't mean that you cannot predict accurately. You can still predict at a macro level accurately. At a subatomic, single atom level, you cannot predict. That's what quantum mechanics says. So there is cause and effect. There is also chance, probability, and statistics. So this is the next characteristic of science. The idea of chance is not alien to science. So it's not that if you talk of chance, that it's not scientific. It can still be scientific from the examples I have given. Now, this is the great thing about the scientific method, independent of individuals. I've already spoken about this. Most of you might not have heard of John Bell. There was a big debate between Niels Bohr and Einstein about some complex idea about quantum mechanics. John Bell actually devised an experiment to prove, that only one of them can be right, and his experiment finally proved that Einstein was wrong. Okay. Now, the great thing about science and scientific method is that it is not attached to a dogma. Only because Newton said something, we cannot say he will never be wrong. Only because Einstein was the greatest scientist that the world has ever produced, doesn't mean he cannot be wrong. This is where science accepts that if something is wrong, yes, we agree, this part, what Einstein said, this part was wrong. Not about relativity, this was about something else. About something quantum mechanics related concept. Okay? So if they are wrong, if something they have said does not fit the observations, if they are wrong, they are wrong. Science moves on. It's the quest for truth. It's not about dogma. This is something as students you have to understand. That is the progress of science. It doesn't make Newton or Einstein any less of a scientist. They were absolutely great scientists. But if they were wrong in something because at the time that they propounded a theory, facts were not available or new facts came into existence, you have to accept it. So what science does is to include the cause and effect, include the idea of chance, and go on to newer models, go on to explore, and so on. So it's about questioning. It's about scientific thinking is about the quest for truth. It's about, in fact, I have particularly chosen to use this question mark as the title for the last one because it's about questioning, it's about being skeptical. That's what H.N. and Dr. Narasimha always used to say. In fact, I even remember the time when we discussed what should be the emblem for the science forum. And H.N. being, he was very humorous also, apart from being all this rational and all that. So he said, no, questioning is very important, so you should have a question. So I told him that, look sir, if science has answers for everything, then why have a question only? I told him after the question, we should actually have an exclamation mark. Okay, of course, he laughed it off and okay, this became the emblem at that time. So it's not about dogma, it's about a method, it's about accepting facts. Okay. But then what I have not covered here is there are now theories which in fact we were discussing even just before, where if you take Euclid's geometry, there are 4 axioms from which he builds postulates and so on. So if you were to write a circle around all of geometry, these 4 axioms will fall outside the circle. That means you have to depend on something outside the circle to define what is inside the circle. Okay? And a scientist, a mathematician by name Gödel in the 1930s or 1940s proved that to explain anything, you have to finally depend on some things which is outside your boundary of your explanation. So if you want to explain anything about the universe, you have to depend on something which is outside the universe. So that's where now faith, that means you have to believe in something outside that circle for you to explain what is inside the circle. So there's a big theorem, it's called the impossible theorem or something like that. Okay, Gödel, G-O-D-L. I mean, it's a coincidence that his name, the first three letters of his name spell God. Okay. So now scientists are saying, yes, there are also the concept of entanglement, where it says if two particles, subatomic particles, which are generated or which are created at the same time, if they go away, even if they go away millions and millions of miles, they are somehow connected between themselves. Somehow information between them is shared. Okay, there are experiments going on. In fact, the Large Hadron Collider project in Switzerland is also working on those things. So now things are coming to science and religion, which had gone away in the 1500s. In some ways are coming back together here and there, but a lot more experiments need to happen, of course. But the whole idea is, the whole idea is that you don't have to trust something only because somebody said so. Okay, I think that's what we have to verify it ourselves. And in fact, to end the lecture, I would like to quote from Kalidasa. Puranamityeva nasadu sarvam nachapi kavyam navamityavadyam santa parikshan anyatarad bhajante mudha parapratyayini buddhi. This is my own translation. It says they are not right only because they are ancient, or something is not wrong only because it's modern. Sane men examine and accept. The fool blindly believes what others say. So I want you to have the spirit of inquiry, a healthy spirit of inquiry. Okay, it is not questioning just for questioning's sake, but a healthy spirit of inquiry, a bit skeptical, questioning to understand, not to prove yourself right. Okay, so please develop that habit, and I'm sure you will all succeed. Thank you very much.
Good evening, ladies and gentlemen. It's my privilege and honor to express my sincere thanks to Professor M.G. Vedavyas for giving such a wonderful talk on common sense of science. It has been very informative and interesting, Professor. On behalf of Bangalore Science Forum and all of us here, I propose vote of thanks to Professor M.G. Vedavyas.